In the last video, I talked about the 3 entropy definitions, and I promised I'd talk about the difference between total entropy and molecular or molar entropy. The last video ran a little long, so I cut it short, and I'm going to finish up the total entropy, molecular, molar entropy discussion in this video. So it's really important in this class that you distinguish the difference between total entropy, and molecular or molar entropy, which is some kind of normalized entropy. Normalized. Either molecular or molar entropy. Okay. So first, just to get a picture in your mind, what this means. Let's say I have some sample in a box, and this sample has some kind of complicated compounds in solution. And I do some process on this box, and I measure the entropy. The entropy I get out from this measurement, this S, is a total entropy. This box may have many molecules inside, many moles, many compounds inside the box. And as a result, the entropy I get is not a representation of an individual molecule or individual mole. Instead, it's a representation of the whole box. What you really care about, though, a lot of times is the actual entropy of maybe just one compound. Maybe you want the entropy just of this one compound. Maybe you want some kind of entropy, some kind of molecular entropy. So for one molecule, what kind of entropy do we get? So a big issue people have in this class is when they see the standard definitions of entropy, like I talked about in the last video, they immediately jump to the units. In the statistical definition and the probabilistic definition, they see K Boltzmann, the Boltzmann constant. And the Boltzmann constant has units of joules per Kelvin. If you compare that to the ideal gas constant R, that has units of joules per mole Kelvin. So immediately when they see K Boltzmann, a lot of people assume that whatever entropy measurement I get from a calculation that uses K Boltzmann is a molecular entropy. And that's flat out wrong. If you look at where these equations came from, the statistical definition calculates some value W, some configuration, some multiplicity. And that multiplicity in both cases represents a large collection of particles. So this definition clearly is not a molecular or molar definition of entropy. It's a total definition of entropy. The probabilistic definition is similar. Probabilistic definition calculates the entropy for a system of n particles that are at a probability distribution, some probability distribution p sub I. So both of these definitions are total. All three of those definitions are total definitions of entropy. So if you're using the equations, the entropy you get is a total definition of entropy. That's very important. A lot of times on a question, you might need to deliver the molecular definition. The conversion between these two are very simple. If you have the total entropy, S total, and you know how many molecules you have in the sample. Let's say you have n particles, n molecules. Just dividing by the number of molecules normalizes the entropy, and then you get S molecular, which is the entropy per molecule. Now, if you want molar entropy, you start with S total, Once again, you divide by the number of molecules. Now you have the molecular entropy. And then to convert it to molar entropy, you multiply by Avogadro's number, which is 6.02 times 10 to the 23rd molecules per mole, for 1 mole. And now you have S molar, which is entropy per mole. So just as a reminder, if you're given a question that's asking for molar or molecular entropy, be very careful about the system you're considering. If you're analyzing a system of 1 mole, you may not need to do much to correct your answer. But if you have a system that has a large number of molecules or an irregular number of molecules, you may need to do this conversion to get the correct answer. Thanks. I hope this helped.